Welcome to another lecture on ECEN 215, Principles of Electrical Engineering. Today we are going to introduce the concept of complex impedances. So let's go ahead and get started. So first we're going to do a review of phasors. This was introduced in the previous lectures. So we have here three voltages, V1, V2, and V3 in the time domain, represented here by 15 cosine omega t plus 15 degrees, V2 being 25 volts cosine omega t plus 30 degrees, and V3 being 8 volts times cosine omega t minus 60 degrees. And as we discussed the other day, the reason to represent this in phasor notation is to simplify the concept of this so we don't have to deal with all of these cosine terms when doing general mathematics on these signals. Since we're going to assume all of them have the same frequency and we are discussing AC signals that are periodic by nature, we can represent this in different notation named phasors. So here we have V1 is simply 15 volts, the magnitude, times the cosine of 15 degrees for the real component, and J15 sine 15 degrees for the imaginary component, giving us this 14.48 plus 3.88 J volts, representing voltage 1, and correspondingly for voltage 2 and voltage 3. Again, this is just a review. So to simply add these together, instead of having to go through in the time domain and compute all of this out using trigonometric identities, we can just simply add all the real terms, add all the imaginary terms, and we end up with 40.13, which is these three added together, and then these three added together, so 3.88 plus 12.5 minus 6.93, and we end up with 40.13 plus 9.45J. With phasors, you can represent it in the complex form. Here we have real imaginary, or you can also represent it in the phasor notation form, which is magnitude and phase angle, which if you convert this into that, we end back up with 41.23, which is the magnitude, VM, of the three phasors added together, plus the phase angle, which in this case is the imaginary over the real, take the arc tangent, and you end up with 88.572 degrees. So we also talked about dividing, so that was addition. Subtraction works in a similar manner, of course. Division works by having two signals A and B here, and we want to divide these two, A divided by B, and we just convert to the phasor form, in this case, in the real and imaginary form. We convert them to the phase angle form, which in this case is 15 and 15 degrees, 25 and 30 degrees, and all you have to do is simply divide the two, but subtract the angles. So it's 15 divided by 25 for the magnitude, 15 minus 30 degrees for the phase angle, leading us to a final result of 15 over 25 phase angle of minus 15 degrees, which we simply can just reconvert over to 15 divided by 25 is 0.6 cosine omega t, same frequency, minus 15 degrees. Correspondingly, we can do multiplication in the same fashion as in a little different example. We have 30 and 12 as our magnitudes for A and B. One has a phase angle of 18, the other one has a phase angle of 40. We're wanting C of t is just A multiplied by B. So we convert these to the real and imaginary form, the complex number form. Also, we can look at the phase angle form, which is 3018 and 1240. So we have two different values here, and we just simply need A times B. So this is what we want. You can imagine, since we did subtraction for division, it is simply multiplication and addition for doing the multiplication of phasors. So we're going to take 30 times 12 will be our magnitude, and then 18 plus 40 degrees will be the phase angles added together. And we end up with 360 degrees, say if this was in volts, 360 volts, phase angle 58 degrees. If this was in volts or current, so on and so forth. And then we can easily convert back by just putting it back in the time domain of 360 cosine omega t plus 58 degrees. So let's take a look now at the circuit elements that we have now introduced and what that looks like with an AC signal. Previously, we looked at inductors and capacitors and resistors for that matter with transients being applied. And of course, we've done all our circuit analysis so far with DC circuit analysis being with resistors only. So now let's look at what happens when we introduce an AC signal. So we're going to look at the inductor first. So instead of I of t being a transient where we take it from 0 to, say 5 volts or 5 amps, in the case of I of t being in amps, let's now take a look if we just have a sinusoid component where I of t is some magnitude times sine of omega t plus some phase angle. So everything we just looked at before, but now we're going to apply a sinusoid to I of t. Well, a voltage is still the inductance times the derivative of the current over time. And if we do that, and of course we take, the derivative by parts, we end up with du dt times d sine of u dt, which is simply du dt times the cosine of u, where u, of course, in our case is omega t plus a phase angle. So we end up with, in the end, V of t is equal to Im, the magnitude of the original current, times omega L. So we have the inductance times omega, our frequency, times again. Now notice how the sine became a cosine because of the relationship on the derivative. And then, of course, the u term, if you will, is omega t plus theta. So if you need to review your calculus here, this will be a good moment to do that. So simply we had omega t plus theta as our u. We take the derivative of this, which is just simply the t goes away. We're just really looking at this term, which is omega. And then, of course, since we have L times that, we end up with IML times omega. From this term, the theta is a constant, so that the derivative of that is 0. So that's how we end up with this portion. And of course, the derivative of sine is cosine, and how we end up with this, and of course u just goes back in there. So that's basically it for an inductor. Just visually, so that we can see that, we have I of t as Im sine omega t plus theta, which is this term here, the blue curve. And then we end up with this phase shift of 90 degrees because we went from a sine to a cosine, and the magnitudes is really the only thing that changed. And the magnitude difference is related to L, the inductance, times the frequency. So you can see there's a significant voltage change that's just completely based upon frequency and the inductance. So what happens if we divide voltage by current? Now, if we remember what that really represents, we remember what Ohm's law is. R is equal to V over I. We're going to end up with a value that's basically like resistance. Resistance is a voltage divided by current. So if we divide the voltage by the current, so we have our current here, and we have our voltage. So if we start with voltage and divide by this current, we're going to end up with something. So what do you think that's going to be? I'll give you just a moment here to ponder that. Maybe work that out yourself and see what we get. So let's write our equations in phasor form. So we now introduced all of this new mathematical techniques here of using phasors, because obviously this is in phasor form. We have this cosine. This is what we typically been looking at, where we know the relationship with sine. So now we're going to obviously have something, instead of sitting here doing mathematics with trigonometric identities, we can do mathematics with the phasors that we've learned, because both of them are at the same frequency. What do you think we're going to get if we do that? So let's go ahead and write these in terms of phasors. Im is now just phase angle of theta minus 90 degrees because of the sine cosine relationship. And a V of L is equal to omega L Im with the phase angle of theta. So that's why we have emphasized all of this introduction to phasor math. So we end up with, of course, just to remember, this is sine of omega t. This is just cosine omega t minus 90 degrees. That's how we get this. Now we end up with this equation. V of L, which is this, over Im theta 0 minus 9 degrees, which just gives us in the end omega L because the Ims cancel. And the only thing different is that, the phase theta stays the same. So the thetas basically cancel out in the sense of the subtraction here. And we just end up with 90 degrees. Theta minus theta plus 90 degrees because you're subtracting this term. And we end up with omega L as the only thing left after this division. So the air quotes here, resistance of an inductor, the voltage divided by current is omega L phase shift 90 degrees. This is known as a complex impedance. So we're going to change the word resistance and we're now going to use the word impedance because now we've introduced complex numbers. So just to give the definition, this is straight out of the dictionary. Impedance is the effective resistance of an electric current or components to alternating current arising from the combined effects of ohmic resistance and reactance. And the units are still in ohms. So all we've introduced is this thing called reactance, which is the imaginary component of the impedance. So we still have a real resistance, but now we've added this imaginary value called the reactance. In the case of the inductor, as we just saw, there was no real component. It was all an imaginary. So all of its value was in reactance. And the units are still considered in ohms. So this is why it is critical that you master the phasors coming into this section, and especially in the upcoming section where we're going to actually use complex impedances in circuit analysis. So again, the resistance is the real component and the reactance is the imaginary component. Ohm's law still applies, but we have now changed R so we don't get it confused with the real component resistance to the letter Z. So Ohm's law stays exactly the same. V over I is equal to Z. V over Z is equal to I, and V is equal to I times Z. So everything stayed exactly the same linear relationship between Ohm's law stays the same. Instead of R equal to V over I, we're now saying Z is equal to V over I. Of course, these are all in phasor terms. The advantage of this is all of the mathematics, all of the analysis methods that you have previously learned, the only thing that we're changing is using complex values to do the analysis. So now looking at an inductor, we now know that Z of L, the impedance of inductor, is simply equal to J omega L or omega L shifted 90 degrees. So there's two values that we can use. Remember, we can use the angular form or what is known as the or polar form, and then there is also the rectangular form of this, which is the real plus complex. Well, of course, in this case, there is no real component of an ideal inductor. There's no, actual DC resistance at 0 ohms, but it does have a reactance, which is J omega L. A capacitor, because we could go through the exact same calculus exercise we just did, but I'm just going to tell you what it is. The capacitor is 1 over omega C, with a phase shift of minus 90 degrees. So an inductor is omega L, phase shift 90 degrees. The ZC for the capacitor, the impedance of a capacitor, is 1 over omega C minus 90 degrees, or in rectangular form, its reactance is minus J, 1 over omega C. So a good exercise for you is to go ahead and do the calculus to see that everything works out the same. Do the V of t over I of t to get Z, and you will end up with this set of equations here. So what about a resistor? An actual regular resistor like we have used this entire class so far. Well, as you can imagine, there is no reactance component to an ideal resistor, so therefore Z of R is just equal to R. Fairly easy. So complex impedances can be completely treated like a resistor in your circuit analysis, meaning that you can add all the impedances in series. So you can replace all of your resistors, capacitors, and inductors, the actual elements, with little round or square boxes and just change it to Z's instead, to an impedance value, and then you treat it like you would a resistor. So everything that and elements that are in series, you add, just like you did with resistors. So if you were comfortable doing equivalent circuits with resistances, then you will be able to do equivalent circuits with impedances in the exact same form. So you add all the impedances in series, and of course, parallel impedances are computed just like parallel resistors, where you take 1 over the reciprocal of all of the impedances. Of course, if you have two impedances in parallel, like two inductors in parallel, you will use, Z1 times Z2 over Z1 plus Z2. So that's why it's important, again, to master the mathematics of going back and forth between polar form and rectangular form, and doing all the complex math, being able to add, subtract, multiply, and divide your impedance values or your complex numbers. These phasors will enable you to do this. So again, series impedances add, parallel impedances are computed just like you would with a parallel resistor. And of course, now you can perform steady state AC circuit analysis just like you would perform steady state DC circuit analysis with resistors, but you're now replacing everything with impedance. Of course, it's important to point out in the transient analysis, we did steady state DC circuit analysis, transient analysis, steady state, where we replaced inductors with shorts and capacitors with open. You can't do that here. You have to go through and compute all the impedances, and now all the impedances become basically little boxes with an impedance value, and then you will go through and perform the nodal voltage and mesh current analysis, and we'll be going over that in a later lecture, just like you would previously, but now with complex numbers, these impedances. And here's an example of that, of us computing, taking the circuit elements, converting them over to impedances, and in getting the, if you will, the terminal equivalent impedance. So imagine in an earlier lecture, these would have been all resistors. And so if this was a resistor, and this was a resistor, and this was a resistor, and this was a resistor, we would be asking, what is the equivalent resistance between these two terminals? Now we're asking, given this frequency of 1,000 radians per second, what is the equivalent impedance? So how would we begin this? Well, simply the first step is to convert everything over to its impedance. And remember, capacitors are 1 over omega c, phase shift minus 90 degrees, or also in the rectangular form, minus j 1 over omega c. And inductors are omega L 90 degrees, or in the rectangular form, j omega L. So let's go ahead and do that for this particular problem. So if we do that, we end up with, we have omega is 1,000 and 12.5 microfarads. So we're going to first focus on the rectangular form. So we have 1,000, omega is 1,000, so 1 over 1,000 times the 12.5 microfarads. So take 1,000 times 12.5 e to the minus 6 farads. And then we just simply need to do 1 over that. And we end up with minus 80J. So we'll go ahead and write that down. And I'm going to have a slide where I show this in a second. And then for the inductor, we have 0.1 henries. So it's omega L. So we have 1,000 times 0.1 henries, and we end up with 100. So this is J100. So we end up with minus J80 ohms. Still the resistance has stayed the same, 100 and 200, so that did not change whatsoever. And the impedance for the inductor is plus J100 ohms. So not to get confused with this, we can also convert these little boxes. So we can convert. But first, now that we know this, we can actually convert this first part into an equivalent impedance. So we have a 200 ohms in parallel with a 100 ohm resistor in series with J100. So we can automatically say we know what the impedance of this is because it's series. With series we add, so we end up with 100 plus 100J. And then we're going to have that in parallel combination with the 200 ohms. So in that case, you're going to do the parallel ohm or parallel resistance equation, which is this times, so 200 times 100 plus J100 divided by 200 plus 100 plus J100 ohms, which we could rewrite this as 200 times, in this case it's 100 and 100, so we take the magnitude of that, so 100, 100 square, add, take the square root, that's 141.42 ohms with a phase angle of 100 over 100 arctangent, that's 45 degrees. You can see that automatically. Since these two values are the same, the arctangent immediately is 45 degrees. So this, and I'll go ahead and write this out here. Let's see. We have this combined together leads to 141.42 with a phase angle of 45 degrees. Sorry for the poor drawing here. So we have that, and then we're going to put that in parallel with 200. So we're going to multiply that by 200, phase angle of 0. So we still end up with now 28,284 phase angle of 45. And that's going to be divided by 300 with 100J. So I'm going to go ahead and do that, and we end up simply with 80J 40 ohms for this part here. And now we have that in series with this capacitor. Now this just simply needs to be added together. And as you can imagine, the real stays real, and all we're really doing is adding the complex part. So we're taking plus 40J and subtracting 80J ohms from that. And now we just end up with one device that is 80 minus J 40 ohms for the complex form, or in the polar form of the phasors, 89.44 is a magnitude with a phase angle of minus 26.57 degrees. So we took this much complicated circuit of different impedances and just said if we were looking for the equivalent impedance, we end up with just this. So same process that you have been doing this entire semester so far, but now we've introduced phasors to this and are now using frequency. So it's just some additional steps and some additional mathematics, but the overall analysis process has stayed exactly the same. So in summary, we learned about complex impedances, and of course, and specifically, we learned about the impedance of inductors and capacitors. So now we've taken the concept of phasors, and now we're applying it to the actual circuit components like inductors and capacitors, and also resistors. And as we learned with inductors, it was J omega L is the impedance. This is where the frequency that in phasors so far, we've kind of in the phasor math, we haven't seen omega have an application. This is where omega comes in. So is in the impedance of the inductor and the capacitor. So inductors being J omega L and capacitors equal to minus J 1 over omega C. So it's important to get those equations memorized. And of course, with resistor, the impedance is equal to the resistance. It's all real. There is no imaginary part of the impedance for a resistor, versus where an inductor and a capacitor ideally has no real component, but is completely imaginary. So just make sure you learn those equations because you're going to be seeing and using those equations a lot in the upcoming lectures. So we have the impedance of the resistor, obviously R is equal to R. And then we talked about equivalent impedance. Similar to resistances, work impedance and resistance are kind of hand in hand, the same, especially when we're about to come into circuit analysis in the AC domain. Everything works exactly the same. You add series impedances together, and in parallel impedances, you apply the 1 over reciprocal. So you have 1 over R1 over 1 plus 1 over R1 plus 1 over R2 plus 1 over R, 3, da 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 da, 1 over Rn. So you have n components in parallel. That's the formula you would apply. In the case of two impedances in parallel, you would have, and of course I was using R, it should be Z, Z1 times Z2 divided by Z1 plus Z2. So you're effectively changing R for Z. It all effectively means the same thing, just now you're using phasor arithmetic. So this is a new concept, and I'm sure you probably have some questions of how that works. So make sure you attend the Q&A sessions to ask questions about phasors, the phasor math that we've introduced, concept of AC signals, how to go back and forth between the phasor domain and the time domain, um, dealing with radians per second versus frequency and time, and then of course dealing with this concept called impedance and how to compute the impedances of components and how to come up with the equivalent impedance. Once you've mastered these concepts here, you are set up for being able to do AC circuit analysis, which is our next topic.